Okay, so for my first try using the screen capture technology, I wanted to talk about something that I thought was really neat as a kid. Growing up, I wanted to be an astronaut, and one of the things that you see on any video of an astronaut in space is how they can float. And here we actually have a picture of two astronauts, and the one astronaut is showing how they can move this big, heavy person with just their fingertip, move them up, move them down. And that's an interesting thing to try to understand. Now, there are a few words that you hear when talking about this in outer space that really are some words that we need to think a little bit about to understand why is this actually happening and how is it that we can recreate weightlessness on Earth, which is what was done, in fact, in the movie Apollo 13. Those scenes with the astronauts floating in the Apollo space capsules were filmed on the Earth or very close to the surface of the Earth. So the words that are used quite a bit in describing this are microgravity and weightlessness. And they're two words that are generally used when we talk about flying in space. However, they may not, their definitions are not very precise. I know growing up, when I heard the word microgravity, I thought of the um, space being a place where gravity was very, very small, and that's why people didn't fall. They were just floating there. And weightlessness kind of brings about the same ideas of two people floating in space because they don't have any weight. Well, let's make some observations about what in fact is going on in space and see if we can define microgravity and weightlessness a little bit better. Okay, so the first idea is microgravity. Does that mean that in fact in space, when they say it's a microgravity environment, there is no gravity whatsoever? Well, here in Exhibit A, in the first bit of the PowerPoint, I show that the Earth and the Moon are in fact 240,000 miles apart from each other, but the Moon is orbiting the Earth um, because the Earth is pulling on the Moon through the gravitational interaction. In Exhibit B, I show our Red Bull jumper jumping out of a balloon that's 21 miles up, and gravity is pulling the person down. So the force of the Earth is pulling the person down because of the gravitational interaction. So we know that there is definitely gravity 21 miles up from the surface of the Earth, and it's big enough to get this guy to fall to the Earth, and the gravity between the Earth and the Moon is strong enough that the Earth is able to keep the Moon orbiting it. If we go to the third slide, is there microgravity on the ISS? Well, the ISS is pretty high up, but it's 420 miles above the surface. But when you compare that to the radius of the Earth, you see that it's actually really not that big of a distance compared to the radius of the Earth. And so, thinking about it, you can think, well, I don't really think gravity is going to end when I get right off the surface of the Earth. So it's believable to think that the Earth is still able to pull on the space station when it's just 420 miles above the surface of the Earth. So when the word microgravity is used to describe people floating in space, it's not they're not saying that there is no pull of the Earth on the objects in space. In fact, it's probably not that much smaller than the pull of the Earth on these objects if they were on the surface of the Earth. So the Earth is pulling on the ISS and all the astronauts aboard. Um, so, right, again, microgravity cannot mean that floating is caused by a decrease in the strength of the gravitational interaction because it's reasonable to think that gravity is still pulling on the objects there. All right, so let's take another step here. What would happen if there was no gravity in space? The ISS would just be floating there. There's no Earth nearby, and it would move, okay, a certain distance every 15 minutes. If we put gravity back in and we have the ISS there, but it's not moving sideways at all, after 15 minutes it would fall closer to the surface of the Earth. And after 30 minutes it would be even closer to the surface of the Earth because it's in free fall. and eventually it would, hit the ground. But if I mix the two so that the ISS moves and it's in free fall, we actually get a shape where the red dot shows the path of an orbit of the ISS around the Earth. And if you can imagine it continues around, the ISS is actually in a continuous state of free fall towards the surface of the Earth. But because it's moving sideways and because the Earth is round, in fact, it never hits the surface of the Earth. So you can think that what's happening here is the ISS is continually falling towards the ground, just like I could, you know, skydive and fall towards the ground. However, when I skydive and I'm falling straight down, I will eventually hit the surface or pull a parachute and get to the surface. But because in the ISS you're moving fast enough sideways, and because the Earth is in a circle, I can be in free fall and never hit the ground. And that's the special thing about an orbit. You need to get the speeds just right to make it work. But if you do get it to work, you can be in free fall for days or weeks or months or even years or forever. Like the moon has been in free fall for 5 billion years. So that's what you can think of, that the astronauts are actually experiencing an extended free fall. And I have a little video of how this can actually happen on Earth. You both know that the movie Apollo 13 was filmed by putting the actors inside a plane called the Vomit Comet. And that plane flies a special path so that during part of it, um, the people inside are in free fall, and the plane is in free fall. It's falling at 9.8 meters per second squared. And when this happens, you have people, looks like they're floating in Earth. So you can actually recreate this experience on Earth. Now, let me jump back to my slide here. And we've got both a person and an apple aboard the Vomit Comet. They're both falling to the Earth. Now, the reason they seem to be floating is because when an apple and a person are in free fall, they both fall at about the same rate if you don't worry about the effects of air on the person. The guy is going to fall at 9.8 meters per second squared, and the apple is going to fall at 9.8 meters per second squared. So you can imagine if you were to look at something as you're falling that's next to you, it would appear to be floating next to you. Just like if you've seen videos of people skydiving, when one person is falling and you look out at a person next to you who's also skydiving, they appear like they're floating next to you. Well, this is what this person is seeing with the apple. And so weightlessness is actually the reason that they're considered weightless is because if you were in free fall and you tried to stand on a scale, the scale would give you a reading of 0 pounds because it's also falling and it's not going to push back up against your feet. So you are weightless in space because you can't be weighed on your traditional scale. So that's really what weightlessness means. It doesn't mean that the Earth is not pulling on you, because in fact it is, and it's causing you to be in this state of free fall forever. So if we can just talk about these words again. So weightlessness is a word. Well, can you weigh yourself in space by standing on a scale? No. So that's why they say a person in space is weightless. It's not because the Earth isn't pulling on them. And the word microgravity describes the sensation that the astronauts are feeling in space. They feel like there is nothing pulling on them, when in fact there is, but it's as if there was no gravity. But in fact, microgravity does not correctly describe what's going on in the physics, because in fact the Earth is pulling on them. It's just the orbit was worked out perfectly so that they're in this extended free fall that lasts for days and weeks. So there are some couple words that kind of help describe what's going on when we talk about weightlessness and orbits. Okay, so I will talk to you both later.